First we'll see the beam column with concentrated lateral load. Consider a simply supported member of length L that is simultaneously acted on by a transverse load Q and axial forces P as shown in the figure. Then we take a section at the midpoint at a distance x from the origin, that is from the left hand side. So we have axial force P acting on both the sides, as well as the internal moment resistance, that is minus EI y double dash, and the deflection at the distance x is taken as y, and we also have Q by 2 distance force. Now we have the external moment at distance x from origin as m is equal to qx by 2 plus py, and internal moment resistance, as already said, minus EI y double dash. For equilibrium, internal moment has to be equal to external moment. Therefore, equating both, we get EI d square y by dx square plus py is equal to minus q by 2x. We further divide the whole equation by EI, and then we get d square y by dx square plus k square y is equal to minus qx by 2ei, in which k square is substituted as p by ei. The above differential equation can be solved, and the general solution can be obtained as y is equal to a sin kx plus b cos kx minus qx by 2p. Minus qx by 2p, that is the last term, is the solution for the particular part which is there in the right hand side of the differential equation. Now we apply the boundary conditions to find the values of arbitrary constants a and b. Since it is a simply support at the ends, we have at x it is y is 0, that is the deflection is 0. When these values are substituted into the main equation of y, we obtain b as 0. Next, we also know that at the midpoint of the beam, the slope is 0 since the tangent goes parallel to the beam. Therefore, we have y dash as 0. When this boundary condition is substituted into the equation of y, we obtain a as q by 2 kp into 1 by cos of kl by 2. Substituting the value of a and b into the main equation of y, we obtain y is equal to q by 2 pk into sin kx by cos kl by 2 minus kx. Now we also know that the maximum deflection is occurring at the midpoint, that is x is equal to L by 2 and y is equal to delta. So therefore delta is equal to, we obtain that q by 2 pk into sin kl by 2 upon cos kl by 2 minus kl by 2. Now sin by cos is tan, and we assume u is equal to kl by 2. Therefore we get delta is equal to q by 2 pk into tan u minus u. Multiplying the obtained equation and dividing the same equation by L cube by 24 EI, we obtain delta is equal to QL cube into 24 EI divided by 48 EI into KPL cube into tan u minus u. After resolving, the final equation that we get is QL cube by 48 EI into 3, the whole bracket opens, tan u minus u divided by u cube. Since we know that for a point load acting on a simply supported beam, the deflection is QL cube by 48 EI, we can take it as delta naught. Therefore, the equation of delta becomes equal to delta naught into 3 tan u minus u by u cube. To further simplify the expression for delta, let us make use of the power series expansion of tan u, which is tan u is equal to u plus u cube by 3 plus 2 by 15 u raised to 5 and goes on. Substituting back into the equation of delta, we obtain delta is equal to delta naught into 1 plus 2 by 5 into u square plus 17 by 105 into u raised to 4 plus goes on, where u square is equal to p by ei L square pi square by 4 pi square, which can be solved and we obtain as 2.46 p by pcr. Therefore, substituting back into the equation of delta, we obtain delta is equal to delta naught bracket opens 1 plus p by pcr plus P by PCR square plus P by PCR cube, and goes on. Since the sum of the geometric series inside the bracket is 1 by 1 minus P by PCR, we can substitute it back and we get the shorter term, that is delta is equal to delta naught into 1 by 1 minus P by PCR. Now we'll see the bending moment part in the member. As we know, the maximum bending moment occurs at the center of the span, which can be written as QL by 4 plus P into delta. As we have calculated the value of delta in the above, we substitute the value of delta back and we obtain M max is equal to QL by 4 into 1 plus PL square by 12 into 1 by 1 minus P by PCR. We further solve it and the final equation that we get is that M max is equal to QL by 4 into 1 minus 0.18 P by PCR divided by 1 minus P by PCR. Let M naught is equal to QL by 4, which is the maximum bending moment, triangular in shape for a concentrated load QL by 4. We substitute back into the M max and we obtain M max as M naught into 1 minus 0.18 P by PCR divided by 1 minus P by PCR. The above equation shows that the effect of axial compression on the bending moment is very similar to the effect that an axial load has on the deflection. The conclusions that are derived from this derivation is, the equation indicates that the maximum deflection of the member is equal to D naught, the maximum deflection that would exist if only Q were acting, multiplied by an amplification factor that depends on the ratio P by PCR. The resistance of the member to lateral deformation vanishes as the axial load approaches the critical load. It is thus possible to determine the critical load of a member by finding the axial load at which its bending stiffness vanishes. Now we are going to see the second part, which is the beam column analysis with distributed lateral load. Similarly, we consider a simply supported beam of member length L that is simultaneously acted on by a distributed lateral load W, axial forces P as shown in the figure. The strain energy that is stored in the member as it bends is given by U is equal to EI by 2 integral 0 to L d square y by dx square the whole square into dx, and the potential energy of the external loads is given by V, which is equal to minus W integral 0 to L y dx minus P by 2 integral 0 to L dy by dx the whole square into dx. Thus the total energy of the system is given by U plus V, which is obtained as EI by 2 integral 0 to L d square y by dx square the whole square into dx minus W integral 0 to L y dx minus P by 2 0 to L dy by dx the whole square into dx. To satisfy the boundary condition, the deflection y is assumed to be of the form y is equal to delta into sine pi x by L, which is in the form of a curve, which is different from that as of the concentrated load where we have a straight line. Now since it is a curve, we assume it as y is equal to a curve, it is a function of sine, where delta is the midspan deflection, which is the maximum deflection. Substitution of this y into the expression, we obtain the RHS as EI delta square pi square by 2L raised to 4 integral 0 to L sine square pi x by L dx minus W delta integral 0 to L sine pi x by L dx minus P delta square pi square upon 2L square integral 0 to L cos square pi x by L dx. We know the definite integral formulas is 0 to L sin square pi x by L dx can be given as 0 to L cos square pi x by dx is also given as L by 2. And we also know one more formula, that is integral 0 to L sin pi x by L dx is equal to 2L by pi. Using these definite integrals, we get U plus V is equal to EI by 4 delta square pi square by L cube minus 2W delta L by pi minus P delta square pi square by 4L. For the system to be in equilibrium, the derivative of u plus v with respect to delta must vanish. That is, differentiation of u plus v should be equal to, with respect to delta should be equal to ei delta pi raised to 4 by 2 L cube minus 2WL by pi minus pi delta pi square upon 2L is equal to 0, from which we obtain the value of delta as 4WL raised to 4 upon pi into 1 upon ei pi raised to 4 minus p pi square L square. We multiply and divide the obtained equation by 5 into 5 divided by 384 ei, and we obtain delta as 5WL raised to 4 upon 384 ei into 1536 ei upon 5 pi into 1 upon ei pi raised to 4 minus p pi square upon L square, which reduces to delta is equal to 5WL raised to 4 upon 384 ei into 1 by 1 minus p by PCR. The left-hand factor in this relation is the deflection that would exist if the lateral load W were acting by itself. Thus, we let delta naught is equal to 5WL raised to 4 by 384 ei, which is the formula for UDL acting on a simply supported beam. Therefore, we obtain delta is equal to delta naught into 1 by 1 minus p by PCR. Now we consider the maximum bending moment on the member, which can be given by Mmax is equal to WL square by 8 plus P delta, and substituting the value of delta, we get WL square by 8 into 1 plus 5 PL square by 48 ei into 1 by 1 minus P by PCR. Simplifying the term inside the brackets, we finally obtain Mmax is equal to WL square by 8 into 1 plus 0.03 P by PCR divided by 1 minus P by PCR. The term outside the brackets is the maximum bending moment that would exist if no axial force were present. If one lets m naught is equal to WL square by 8, that is the maximum bending moment for a UDL on a simply supported beam. Therefore, we get Mmax as m naught into 1 plus 0.03 P by PCR divided by 1 minus P by PCR. That's all for today's tutorial. Thank you for watching it. Do like it if you like it. Thank you.